Okay, so in part B of gravitation and satellites, we're going to look at the theory of satellites in circular orbits. So let's talk about satellites moving in circular orbits due to, obviously, gravity, which is the force that causes the centripetal acceleration for a satellite, which is what we're talking about here in this first point here, and is really covered by these first two intended student learnings here. So we know that we've already looked at cases where a tension force and the banking angle provides the force for centripetal acceleration. So in this case, our centripetal force is going to come from gravity. So gravity will provide the force for centripetal acceleration. So hopefully you can see we've basically got a derivation going here, and so what we're doing, we're deriving this formula here, and we're going to equate these two formulas. Just go back to my pen. So we know that the force causing centripetal acceleration is given by mv squared on r. So let's assume there that r is like the mass of a satellite, is equal to the gravitational force, which is equal to g. We're assuming something, in this case, is spinning around the Earth, but it could be any other large object. So that's given by that formula there. We can see immediately that we've got mass on both sides, so the mass is going to cancel out. So the velocity is not going to be dependent on the mass because it's not going to be a term in this equation. We can also see this r here will cancel out one of those r there, because r squared is basically saying r times r. So this is saying r on its own, so r to the power of 1, so we can cross out the squared with one of those r's. So that leaves us with the velocity squared equals g mass of the Earth divided by r. So if we want to get velocity on its own, it's equal to the square root of that. So really what I've just done there is derive that formula for a satellite moving in circular orbit due to gravity. The second thing I want to look at, just on that one as well, and I covered this as I went through, but just to be really explicit about it, demonstrate an understanding that the speed and hence the period of a satellite moving in circular orbit depends only on the radius of the orbit and not the mass. Well, the mass of the satellite is not an equation, not a term in this equation. It cancelled out in this stage up here. So the mass of the satellite is going to have no effect on the velocity. The only things that affect the velocity of the satellite are the mass of the planet that it's orbiting around and the radius of the orbit. Okay, the bottom one here says solve problems using the equations v equals square root of gm on r and v equals 2 pi r on period. So basically it's mainly about problem solving. But what I'm going to show you is another derivation, which is one that you will commonly use or need to do and helps you understand how you do these problems. And it's another one where we equate things. So we know that the velocity is equal to gme on r, but we also know for an object moving in circular motion that velocity is equal to 2 pi r on period. And one thing that we're often interested in is what is the period, so how long does it take a satellite to do a complete revolution? So we're going to equate these two here. So we're going to go, obviously the GME on R is equal to 2 pi R period. Now the square root there is a little bit of a pain and it makes it difficult. So first thing we're going to do, and no, I'll just keep this in the same colour. I'm going to square both sides, because by squaring both sides, that gets rid of that square root. So we get left with GME on R is equal to 2, we'll do this now. 2 squared is 4, pi squared is pi squared, R squared is R squared over the period squared. So I've just squared out everything that was in that bracket. Now, as I said, the thing that we're normally most interested in is getting period on its own. So we're going to do a little bit of algebra here. At the moment, period is on the bottom, which is a bit of a pain. We want to get it to the top. So I'm going to times both sides by the period squared. Then that cancels. Now, I want to get rid of all this stuff on this side. So let's get rid of the R on the bottom. We'll times both sides by R. So R times R squared is eventually going to give us R cubed, but we'll do that in the next line. And that R over R cancels. We've got the mass of the Earth here, we're going to get rid of that. So we're going to divide both sides by the mass of the Earth. Oh, so I already cancelled that at the top, so that cancels that. And I want to get rid of the gravitational constant, so I'm going to divide both sides by G. And that's going to leave us with, when we simplify all that out, we'll go back to the green. Period squared equals 4 pi squared R cubed on mass of the Earth times by gravitational constant. Now, I know I haven't quite solved problems using that, but if you understand that process and that sort of algebra, I think you're going to be able to tackle any of the questions you get there. And as I said, one of the common questions that you'll get is around using the period. So I think that's valuable to see that derivation there.